Hello, everyone. Nice to see you guys. How was your weekend? Okay. Do you hear me now?
Yes.
Oh, okay, cool. Was not clear with my microphone.
Good
Good.
afternoon.
Last time during our discussion on Friday, we finished the topic related to linear momentum and also conservation of linear momentum. So the last topic we discussed was rocket propulsion motion, which is based on this concept. So today we continue further with our course, and that is rotation of rigid objects. So we will go through main parameters which define this rotational motion of rigid objects, which rigid means that the distance between points of these objects do not change with respect to each other while this motion is happening. So it's different from translational motion, which we considered so far. So here will be some axis of rotation. So the body will rotate about this axis. Since it's a different type of motion, we need to propose some other parameters in order to describe it. It will be quite similar in conceptually to translational motion. However, parameters will be different. And also we will consider, we'll see with time how it goes. We'll proceed with the consideration of kinetic energy of rotational motion, which also has some features which should be discussed and taken into account. Okay, I believe we can switch to the slides. And if we consider some object and some point, let's call it point P. So this will be the axis of rotation, and the distance from axis to rotation to this point will be, let's call it point O, will be R, radius. So if this body starts to move, let's say, like rotate about this axis, O, then this path of the point of this rigid body, which we mark as S, will be defined as this radius, the distance from the axis of rotation, times the angle theta, which is measured in radians. So this is technically the definition of this radians. So angle in radians is equal to the length of this segment of the circle divided by the radius of the circle. So if we have, for instance, some like full circle, which will be 2 pi times r. So if we divide by r, then it will be 2 pi radians. So 2 pi radians stands for complete, like one complete rotation, or 360 degrees. So in order to describe this rotation around, like about a fixed axis, we definitely need to operate with angular velocity. So we had this introduction of angular velocity previously, but here it's the main parameter which should be used. So following our previous considerations of some kinetic equations, we can also extrapolate those approaches to rotational motion. So first we can consider some average angular velocity, which will be theta final minus theta initial divided to theta t final time minus initial time. So that will be delta theta over delta time. And you may already see from like this part which we discussed here that theta stands for equivalent of x. So theta is equivalent to x position in translational motion. In rotational motion, equivalent to x is theta. This angle of rotation about the fixed axis. So obviously, we don't usually deal with average values. So we want to know instantaneous parameters, and instantaneous angular velocity will be given as a limit. This delta t approaches to 0 of delta theta over delta t. And that is the first derivative of angle theta over time, dt, d theta over dt. So the units for angular velocity, omega, are radians per second. So following the same steps, we need to go further to acceleration, angular acceleration. So let's call it A is equal to limit delta t approaches to 0, delta omega over delta t. So that is first derivative of angular velocity over time, or it is second derivative of angle theta over time. So this is definition of angular acceleration, and angular acceleration is always, so let's start with angular velocity vector. So it is pointed always perpendicular to the plane of rotation. So it's always a long axis of rotation. And according to the right hand rule or the right thread screw rule, you define the orientation of the angular velocity vector. For instance, if we have rotation in xy plane, then this omega vector will be directed out of the plane when the rotation is counterclockwise, and into the plane when it's clockwise. And angular acceleration vector will be always aligned also in these directions. However, it will be either in the same direction as angular acceleration if angular acceleration is increasing, or in opposite direction if angular acceleration is decreasing. So the question is, for instance, why do we have this orientation of angular velocity along axis of rotation? So this is the only option to have some commonly accepted description of the direction of rotation, which describes it uniquely, because we can deal with linear velocity vectors, but for some points of this body. But that's not good approach, because linear velocity vectors will have different orientations, and it will not define in total the rotational motion of all bodies. So it will be necessary to define very many points with different vectors. So in order to define one unique vector, which will describe in which direction, clockwise or counterclockwise, in the given frame of references, this system is rotating, we operate with angular velocity vector, which is oriented along axis of rotation in one or another direction. And the same stands obviously for the angular acceleration vector. So as you may already notice, that there are quite many similarities for like between the kinematic equations between translational and rotational motion. So we already mentioned here this relationship, like equivalence between theta and x. So we have also equivalent parameter for linear velocity. This is angular velocity, and the same also for acceleration. We have a linear acceleration vector and angular acceleration vector. So that's why if we consider some specific case of a rotational motion with constant angular acceleration, then we will have the same, like very similar set of equations for this purpose, and let us write down. So final angular velocity will be equal to initial angular velocity plus this angular acceleration times t. For theta final, we can write that theta initial plus omega initial times t plus component responsible for the angular acceleration will be a times t squared divided by 2. And we also can express time from the first equation, substitute then instead of time in the second equation, and then we will get final angular velocity square is equal to initial angular velocity plus 2 times angular acceleration times theta final minus theta initial. So this is all the same structure as kinematic equation from for translational motion with constant acceleration. But here we just operate with angular velocity and angular acceleration and angle theta instead of x, v, and a. So these are called kinematic equation for rotational motion with constant acceleration, and that's applicable for cases when you need to deal with quantitative analysis of rotational motion of rigid bodies. Okay, so with kinematics of rotational motion is more or less clear. Now we need to consider rotational kinetic energy. So far, we were considering kinetic energy associated with translational motion. So we had this m times v squared divided by 2. Let's say kinetic energy is equal. And in this definition of translational motion, it's absent for rotational motion because for rotational motion, there are no components associated with translational motion. However, particles of the rigid body, which rotates about some axis, they are moving in space with certain velocity vector. And obviously, this rotational motion should also possess some kinetic energy. So let us consider some rigid body. Then we have axis of rotation. So here will be our angular velocity vector. Then this is our radius, Ri, to some one of many points of this body with mass Mi. So its trajectory will be such circle. And here is the linear velocity vector of this point Mi. So it will be Vi vector. So this particular point, like some small volume of this rigid body with mass Mi, in this case, will possess certain kinetic energy. So kinetic energy of this body, of this like part or small part of the body, will be 1/2 times Mi times Vi squared. So this is what we know from translational motion. However, we need to, like, first of all, in order to get the total kinetic energy, we need to sum up all kinetic energies of these small parts of the body. So that will be, let's say, kinetic energy total will be sum for all these small volumes of the body, Ki, and we can write 1/2 Mi Vi squared. However, here at this point, we need to focus our attention because this velocity is not the same for each point of the body. It depends on the distance from this axis of rotation. In order to take this into account, it is obviously convenient to use to represent this linear velocity with angular velocity. And that is some unique feature which describes whole body at once. So we don't need to consider each point separately because it comes also from the fact that this is a rigid body. So we assume that point distances between all points of the body don't change. And that means if one point is rotating about axis of rotation with angular velocity omega, means that every point of this body, regardless of its location, will also rotate with the same angular velocity on average and also instantaneously. So in this case, we can write the following. Let's put this 1/2 in front of the sum. And here will be mi times ri times square times omega square. So omega is the single parameter for all points. We also, if we continue, so we can write in such form here, 1/1/2 times this sum for mi times ri square, and here is our omega square. So this is the unique feature of the body and the axis of rotation, because we operate here with the mass of small elements of this body and the distance of these small elements of the body. So it takes into account shape of the body and also position of the axis of rotation. Because if we change position of axis of rotation, if we start to rotate about other axis, then of course distances from this new axis to all other points of the body will change. So that's why this parameter is called moment of inertia. Let's call it, like, mark it as I, capital I. And this moment of inertia is a unique feature of the body and is defined like body axis combination. So it's always defined with respect to certain axis of rotation. So you cannot determine this parameter just in general for body, because you always need to define the position of the axis of rotation. So in this case, we can write that total kinetic energy of the rigid rotating body will be equal to 1/2 times I times omega square. So you see now the equivalent of mass in rotational motion is moment of inertia, I. So we have for translational motion m times v squared divided by 2. And if we substitute linear velocity with angular velocity, then we operate with a moment of inertia and have the same form of equation, but with other parameters involved for kinetic energy of rotational motion. So what is important to know, like, first of all, this, since we introduced this new parameter, moment of inertia, units for this will be kilogram times square meter. And we need to highlight that it's additional form of kinetic energy, which can be present in the case of a moving body. So if we have some body on certain height, so it will definitely possess some potential energy. So total energy of the body will be equal to m times gh, which potential energy. Then if this body performs some translational motion, then we need to sum up the kinetic energy of associated with translational motion, which will be m times v squared divided by 2. And in addition, if this body also rotates about some axis of rotation, we need to consider contribution from this rotational motion to the total kinetic energy here. It will be moment of inertia with respect to this specific axis of rotation times omega squared divided by 2. So this we need to remember and take into account when we deal with some cases which includes both translational and rotational motion. So let us consider some examples of calculating this moment of inertia. Let's start from something simple. We have some axis x and y system of coordinates and such a system of 4 bodies. So with mass m, and here are heavier bodies, capital M and capital M. So the distance here and here, they are the same. So the distance A, and also here and here, this distance is B. So now there are different options for rotation. We can rotate about axis Y. We can rotate about axis X. And also we can rotate about axis Z, which goes into the plane of the image. So it will be kind of rotating like this. So since we have different axes of rotation, we need to calculate different moment of inertia for each of these cases. So let us consider first moment of inertia with respect to the rotation about axis y. So we know that moment of inertia is the sum for all masses times distance to the axis of rotation in square. And now if we neglect with the size of these bodies with respect to these distances, so we assume that size of the bodies is much smaller than the distances from the bodies to the axis of rotation. So we kind of operate with them as mathematical points. Then we see that these masses, which are like 2 bodies which are located on axis y, do not contribute to the moment of inertia Iy, because the distance from axis y to these bodies is equal 0, because they are located on this axis. So only bodies with mass capital M located on axis x will contribute. So it will be m times a squared plus another body will be m times a squared, which will be 2 m times a squared. So this is the moment of inertia of this system of four bodies with respect to axis y. Now, if we want, for instance, to consider kinetic energy, we can also calculate it. So let's say kinetic energy for such rotation with some angular. Let's assume that it will rotate with the same angular velocity about all axes. So it will be 1/2 times iy times omega squared. So here we get 1/2 times 2m a squared times omega squared. And eventually we get m times a squared times omega squared. So that is kinetic energy for this rotation about axis y. If we consider rotation about axis x, then it will be equivalent situation because these two bodies with mass capital M located on axis x will not contribute to the moment of inertia, since the distance to the axis of rotation for these bodies will be equal to 0. So instead of this capital M, we will put these smaller masses in order to get Ix. So it will be equal according to this the same approach. It will be 2m times b. So b is the distance from axis x to these small bodies located on axis y. And the same will be for kinetic energy. Now let us consider the case when all bodies contribute to the moment of inertia, and that is this case when we have rotation about axis z. So in this case, all bodies need to be taken into account since they have certain distance to axis z, to origin of this coordinate x and y, and obviously they will define the moment of inertia. So Iz is equal to the sum for all masses and times square distance. And that is equal to ma squared plus ma squared plus mb squared plus mb squared. So all bodies contribute. So we will get eventually 2ma squared plus 2mb squared. So we see that for all axes of rotation, we get different values of moment of inertia, which is a good example that we cannot define moment of inertia without defining axis of rotation first for any given system. So this was an example for the case with a system of many bodies. However, we may usually also deal with some continuous bodies. And in this case, we need to go for some limit, and moment of inertia in this case will be considered as following. So it will be some limit delta m approaches to 0. So we will consider very small parts of these continuous bodies of this equation. Here it will be sum for all these small masses, their distances to axis of rotation times this small mass. So that is nothing else as integral of r squared dm. So d m can be considered as depends on the system, on distribution of mass there. It could be like three-dimensional, two-dimensional, one-dimensional. So we can write dm is equal rho, its density, times small volume. dm can also be defined as sigma, surface density, times d a small area, or can be defined as dm, which we did also earlier, lambda linear density times dl. So these are options to define this small mass for different cases. And let us consider some examples of these continuous bodies. So here we will deal with some rod, so it will be kind of one-dimensional case. We have axis x, axis y. Here is our rod with the length L. We will calculate for this given configuration the moment of inertia of this rod with respect like axis y. So this direction of rotation. So we can define dm as lambda times dx. Lambda we assume constant, so we can write another way. It will be total mass of the rod divided by the length of the rod times dx. So moment of inertia I y will be equal to integral of r squared dm, as we defined earlier. And now if we go from dm to this expression, it can be written already in the following form: minus L over 2 plus L over 2. So these are ranges of our integration. So here is minus L over 2. Here is L over 2. Times x squared m divided by L dx. So m divided by L, these are constants. We can take them out from integral. We will have here x squared dx. So when we integrate this, we will get m over L times x cubed over 3. And this will be in the ranges minus L over 2 plus L over 2. So when we substitute these values, we will get the following. So here will be 3L, L cubed over 8 minus, and here will be another minus L cubed over 8. So now minus and minus will give us plus. So we will get m over 3L times L cubed divided by 4. L and this cube we can cancel, and eventually we will get m times L divided by 12. So this is a moment of inertia of this rod, a continuous rigid body with respect to axis y. When axis y goes through the middle of this rod. So do we have more time? Let us maybe. Oh, yeah, you're right. Thank you. We forgot this square here. So let us consider one more example, which will be in kind of three-dimensional case. So will be some cylinder. Let's say this is some axis Z. Here we have some cylinder, which is filled, and the height of this cylinder, let's mark it as L, and here is the radius of the cylinder. So in order to proceed here, so dm is density, which is considered to be uniform, times dv. And dv, we need to define it in order to make it convenient for us. So we can go for some system like this. So here it will be radius r, and this distance, the thickness of this internal cylinder, which we consider will be dr. So in this case, this dv, some elementary volume of this cylinder, would be considered as the length, like the area of between these two circles internal. So it will be 2 pi r, the length of the circle, times dr. And that should be also multiplied by L, by the length of the cylinder. So that will define us some like very small volume of this cylinder, which we will deal with, which will give us this dm. So then we can write dm is equal to rho times L times 2 pi r times dr. So this is the expression for very small element of mass of this cylinder. And let us consider, like calculate the moment of inertia of this cylinder with respect to axis z. So our general equation, r squared times dm integral. Instead of dm, we substitute this guy. It will be integral r squared rho times L times 2 pi r. I think we don't need maybe this. R times dr. And this part is constant, rho, L, and 2 pi. So we take this out from the integral. So it will be 2 pi rho L, integral from 0 to the radius of our cylinder, R, capital R, times R cubed dr. So here we can already integrate this. So it will be 2 pi times rho L times R in the force power divided by 4 from 0 to R. And this is equal to 2 pi rho L times R in the power of 4 divided by 4. Here and here we cancel and eventually get pi times rho times L times R in the force power divided by 2. We can also express rho like density. So that will be rho is equal to total mass of cylinder divided by its volume. So it will be total mass divided by pi r square times L. So this is the area of the base of the cylinder times its height. And if we substitute now this instead of rho here, we will get the following. So it will be 1/2 times pi mass of the cylinder divided by r PR square L. This stands for the density times height of the cylinder times R in the force power. And here we can cancel out the height of the cylinder. We can cancel this R square and here force power. We have only second power and also this pi. So eventually we will get m times r square divided by 2. So this is the equation for the moment of inertia of this cylinder with respect to axis z. So we introduced during this discussion the concept of initially we introduced the kinematic equations for rotational motion of rigid bodies, in particular considering constant angular acceleration. So introduced also concepts of kinetic energy of rotational motion, which is defined as product of omega square and moment of inertia, and in details discussed how we can calculate moment of inertia. So obviously we need to first define the axis of rotation, and with respect to that axis of rotation, taking into account the shape and density distribution of these bodies, we can calculate moment of inertia, which is necessarily step to calculate kinetic energy of rotational motion. Okay, thank you very much for attention. You have any questions? You're welcome.
Yes. Can you please show the equation for limit equation of inertia Z in page 118, I think.
Okay. You mean this one for moment of inertia?
Yeah, thank you.
Mm-hmm. Okay, then, if there are no more questions, thank you very much for attention. Have a good day. Take care and see you on Wednesday.
Thank you. Goodbye.
Thank you. Goodbye.
Mhm.